Okay, we'll get started. So yes, midterm grades were posted. Unless some of you have not gotten your grades because you took the exam with CAE, and I just got those back today, and so I still have to grade those. So I just have a handful of grades left. If you see your grade and you are happy with your grade, then be happy with your grade. And if you are sad about your grade, then that's also okay. You know, there's plenty of opportunity to do better, and you know, the midterm was worth only 15%. And I say this every single time, but your grades are never a measure of who you are or anything like that, right? Nothing in academics, you know, determine your worth, okay? And people are always curious what the average grade is and all of that, and if I don't want hearing the average to make you suddenly feel good or bad, because you should be happy about your own grade, okay? That's okay. The median was a 98. When I was grading, I was like, oh, well, I guess I made the exam very fair, which is fine. You know, everybody gets a good, not everybody, but over half the class got over 98, and you know, good for you. So so that's fine. But you know, don't. You know, if you got like a 90% and you were happy about that, be happy. Don't be sad that it's below a 98. Okay? It's just there were only 3 problems, so if like one problem gave you a little bit of trouble, you know, it's going to knock your grade down. That's just the nature of that. Okay, let's we're going to continue on talking today. We are in chapter 2, and we're looking at maximum likelihood estimation, and so we're going to take a look at a couple of topics. One is the bias variance trade-off. Okay, and this is kind of a topic that appears frequently in kind of supervised learning problems. Okay, the bias variance trade-off. And you'll see, like, if you search for this on YouTube, you'll find like hundreds of videos on this topic, and you watch each of them, and it all sounds like everyone's talking about different things, even though we're all talking about the same thing. This is kind of the idea is how flexible should you make your model, and you know, are you going to overfit, right? So this is the essential question, right? How flexible do we want to make our model? And you know, will we overfit the data? Will we have too much, I'm going to just call this wiggle room. It's a very non-technical term, but that's kind of the idea here. All right, so we might have, so we often say that the bias variance trade-off is kind of the balance for our, the squared error, the total squared error, right? So, so let's say, let's pretend we know the exact, the true parameter values of the model, okay? So if we know the true parameter values of the model, we can estimate how different are our models parameters from the true parameter models, right? So then we can compare our estimated parameters to the true values, okay? And we can say, all right, what is the expected squared error between the true values and what is the expected error between the true values and estimated values? Okay, and so this expected square error, which we will call the book calls it M bar. Okay, this is going to be equal to, this is the bias squared plus the variance. Okay, so what is this trying to say? Let me just expand this just a tiny bit. It's already February. I don't know what's happening. Time just keeps going, right? I remember when last year started and I was like, oh boy, this is going to be a long year. And then it was over, and now it's 2018, and now it's February, and I guess the clock doesn't care. It's going to go. All right. So okay. So let's say we had the true parameter values W, right, and then our estimated parameters will be W hat, right? Something like that. Okay, and then so if we're talking about what is the expected difference between W and W hat, the expected squared difference between W and W hat, what I'm saying is this is going to be the bias of W hat squared plus the variance of W hat squared, or not, just the variance of W hat. Okay, so the bias, what is the bias of some kind of parameter value or a parameter estimate? This is going to be the expected difference between W hat and W. So what's the expected difference between W hat and W? So if your estimates in the long run are going to, be centered around something other than the true values, we'd say you have biased estimates, right? So an example is if you took the average squared distance from the mean, you would get a biased estimate of the population standard deviation. So if you do, square distance from the mean divided by n rather than divided by n minus 1, on average, you would get a value that underestimates the population standard deviation. okay? Because you're not taking into account the loss of the degree of freedom by using the samples mean as the estimate of the population. Okay. So you have that, and then the variance of your estimates, W hat, this is going to be, you know, the expected difference between W hat minus the expected, so the, what is kind of the average squared distance from the mean, right? And this, probably from 100B you learned, this is W hat squared minus okay, and so the variance is just the variance of our estimates. Okay, so you could, so here's an example. All right, so let's say you have data that looks, I don't know. I'm just making stuff up here, okay? Now we could look at this and we can say, all right, let's try to fit, I don't know, so we have a few choices, right? So we'll say choice 1, linear model. We would do this and we would go, I don't know, this is something like that, okay? And we look at this and we go, ah, that's not a good model. Or maybe it's okay, right? All right, and then another option is, all right, so choice 2, we can do, I don't know, cubic, something? All right, and maybe we get something like that. Maybe that's not that great either. Or, I don't know. Doing my best here, guys. All right. All right, and then all right, and then choice 3. I don't know, something even more complex. All right, and this could maybe fit a lot of the extra wiggle. Or something like that. I don't know. All right, I mean, whatever here. Okay, and we could ask, what is the true model? Okay, the true relationship could be, I don't know, something like this. Now everything's blurred together and you can't tell anything apart, but okay, there could be a true model, right? The true relationship. And so the bias is kind of the idea of, you know, how different is our estimated model, right? So the linear model has quite a bit of bias, right? Okay, in that kind of the true relationship does not quite match up with this estimated relationship. No. Closely match the estimated relationship. Okay. On the other hand, the super complex model, if we look at any, like kind of, this is not really how we measure the bias, but if we look at where the true thing ends up and what the super complex model is predicting, there's actually not too much variance between the true values and the very complex values. Okay, so on the other hand, the very complex model has low bias in that the true relationship and estimated values, so yeah, true relationship and estimated do not vary much, do not differ much, I should say. Okay, but as far as variance goes, okay, as far as we could say look at another set of data generated by the true relationship, okay? So we could, let's generate, a new set of data based on the true relationship. Okay, and so, just get something different, right? Okay. If we look at kind of the estimates for another linear model, will just, the two linear models will probably differ a little bit, but not by too much. You're just going to have like, maybe the slope is a little bit steeper, the intercept's a little different, okay? In terms of the variance of the parameters, the variance in kind of your result, you will have very little variance, okay? The linear model will show less variance, okay, for, fitting, kind of another linear model. Whereas the complex model might come up with a completely different set of estimates. Okay, so this will be more variance. And this is kind of the question that you have to balance and mess around with in terms of deciding how complex your model needs to be. All right, and so this frequently comes up because, even for something like the neural network, how many nodes should you have in your hidden layer, okay? And the answer is not quite clear, okay? You can add more nodes in your hidden layer and you'll have a more complex model that might be able to fit your data better. But depending on, you could end up getting something different. And maybe you even noticed this. We had a pretty small neural network for your homework, but maybe you looked at your resulting weight matrix, right? And you got these certain values. And then you asked your friend, what did you get for your weight matrix? And their weight matrix was probably completely different from your weight matrix, right? And that's because this model, as simple as it is, still has a whole bunch of parameters, probably way too many parameters, and so you can end up with different sets of weight matrices that as far as the training data goes, does a good job of predicting, okay? And maybe they perform differently with the test cases and things like that. And so it's not always a more complex model is superior. The more complex model might do a better job of fitting your training data, but you might have modeled something with a little bit, you might have overfit your data is kind of the deal there. Okay, I kind of want to further explore this question of what kind of variability do we get in our estimates, okay? And all right, so let's kind of put this up here, all right? And so regarding our linear regression model, okay, we now include an explicit error term. And and we can think of the error as kind of noise. And we performed a maximum likelihood estimation. And if we think about that, our model parameters that we estimated, our intercept and our slope, they themselves are random variables that are based on the random values that were drawn from the true model, right? Okay, so here, let me just kind of write this down. So the true model is going to be, we have T sub n is equal to W0 plus W1 x plus some error term. And we said errors come from normal model variance sigma squared. All right, so we could have sample 1 is going to have a set of a vector of t and a vector x, right? And then maybe I'll call this t1 and x1. And sample 2 will have some vector t2 and x2, right? And these will produce some values w hat 0 and w hat 1 to maximize the likelihood. And these will also produce another set of w values, right? So these estimates will depend on the random values in our sample. Okay, and because these depend on random values, they themselves are random variables. And if they're random variables, then they have a mean and a variance, and because we're estimating both at the same time, they've got a covariance term. Okay. So our estimates for, intercept and slope have variances themselves. Variances and uncertainties themselves. Okay. Contrast this to when you did least squares regression, when you have a certain sample of data, you get your estimates and there's no variance there. It's just these are the values that minimize the sum of squared residuals. Okay. Here, using the same sample, we get the same values, except these estimates now have uncertainties because they're based on they are random variables themselves. Okay, so what we want to do is, what are the uncertainties associated with these things? All right, is this okay? So we've got, we said T sub n is equal to W0 plus W1x plus epsilon sub n, where epsilon comes from a normal model, 0 sigma squared, okay? And we can kind of write this in vector form. We'll say W transpose x of n plus the thing, and we will say, so we will let the W vector be the true relationship, true parameters in the population. Okay, and we can ask, all right, we get our actual data. What is the likelihood of our actual data? All right, so we're going to say, what is the probability of our entire vector t given x and the true value w and sigma squared, and this is going to be the product of all of these normal distributions, which have which are centered at each value, sigma squared from n equals 1 to big N. And this entire thing, this is a multivariate normal or multivariate Gaussian. Which we can write as big N x times w, where sigma squared is multiplied by the I matrix. Okay, so sigma squared I is a diagonal matrix with sigma squared down the diagonal and zeros elsewhere. Okay, and if we want to write out the this is 1 over 2 pi to the d dimensions, d over 2 norm of the variance matrix raised to the 1/2 and e raised to all of this. Your sigma matrix inverted. Oh, what a mess. Okay. Okay, don't worry about this. Sorry, I wrote it out there, but I'm like, okay, we don't have to worry about that. Let me just talk a tiny bit about the multivariate Gaussian, and then we'll play around a little bit with some code here to kind of illustrate the idea. So let's just think of a two-dimensional multivariate Gaussian. So we can say, we'll have one normal distribution, okay, and then we'll say x comes from here and y also comes from a normal distribution. Maybe y looks like this. Right? If we were to, if x and y are independent, so then their relationship, their multivariate joint distribution would look kind of like, so the x would be over here and the y is over here, and so the x has more variance than the y, so the relationship would look something like this. And I'm trying to draw these are supposed to be concentric ellipses. My attempt. Okay, and if you were to kind of look from one side, it would look like this, and if you look from the other side, it would look like this. So if you were to just sum everything up, you would get a normal distribution that looks like this, and down here you would get a normal distribution that looks like that. Is that okay? And so you get this kind of this bowl-shaped thing. Something like that. And then if we asked for the covariance between x and y, this would be a matrix with the variance of x 0, 0, and the variance of y. This being kind of your matrix sigma. All right. On the other hand, if there is covariance, then you might have something that looks like this. Okay. No, that's not how we do it. How do you rotate this? No? No, that's not what shoot. Undo. Let's try this again. Dang it. All right. I don't know how to rotate it. Okay, I'm gonna just freehand it. It'll look something like this. Huh? Yeah, you'll see some kind of covariance relationship, okay? And again, but if you isolate it just to one variable at a time, you'll still get things that look normal on each, okay? And then the covariance matrix here will be variance of x, covariance of x and y, covariance of x and y, and variance of y. Okay, and so the question is, how much variance exists? And so I wanted to kind of just model what we're talking about here. So I put some code up, and so we're going to pretend that we know the true relationship between x and y, or x and t. And so we're going to say that the true intercept is -2, and the true slope is 3. And as far as the error term goes, the true sigma squared is going to be 0.5. Okay? And I will do, we're going to just sample 20 random values. okay? And then this r equals 20 is how many repetitions I want. Okay, so let me just kind of create a blank plot. This is the true relationship between x and y, as represented by this blue line. Oh, I need to, I put this in the wrong spot here. Okay, here I'm going to just randomly sample some values in x, and then we'll come back to this later. And I'm going to create a thing, and then so I randomly sampled some 20 values of x between 0 and 1, okay? And I'm going to take random values for our error term, okay? So these are going to be normally distributed, and so the errors might be more or less. And so I'm going to just plug these in, and we're going to say that values that we have, we're going to be t is w0 plus w1 times x plus the error terms. So when I plot these, I get these random. Can you see these dots? I made them gray because we're going to do this a whole bunch of times. Okay, and then we'll ask R to fit a linear model between t and x. So it's fitting the gray dots, and then we ask, what are the coefficients did you estimate? And I'm going to just plot this line. And so the best fitting line for this set of 20 random points looks like this. The true line is the blue, but for these 20 random points that we selected, it looks like this. Okay? And if I tried setting the seed to 2, we would get a different set of errors, and the best fitting line there would be different, okay? And here it lines up a little bit more closely. Okay, so I'm going to go ahead and I'm going to just kind of clear out my plot, and we'll have set seed 1, pick out some random values, and then so for each one I'm going to continue using the same set of x values, okay, the same 20 locations on x, but we're adding different amounts of error. And I'm going to just have these plot all of these things, okay? And so you can see these are the 20 locations. You can kind of see columns forming, but we had different amounts of error. Let me just add back the original best fitting line, okay? So the true line is this blue, but we can see kind of 20 different models being fit, and we can see, you know, sometimes the intercept is higher or lower, and sometimes the slope is higher or lower, and whatnot. Okay, and so so the question is, what is the variability of just these different W0 and W1 estimates that we have? Okay, and so to kind of this, because of for the plotting purposes, I only did this 20 times. Okay. But to kind of get a true estimate of the variance of W0 and the variance of W1, I'm going to go ahead and just do this 2,000 times, okay? It's the same thing. Every single time, I'm going to continue using the same set of x values, but each time I'm going to just randomly draw new error values and then generate the values t based on those things, fit a linear model, and then we're going to extract the coefficients and store them in this matrix coefs, okay? So I'll go ahead and I'll do that. We run through all of this, and so I'll have now 2,000, so if I look at the dimensions of coefficients, I've got 2,000 values, and I've got 2 columns, one for W0 and one for W1. So I can look at, you know, what is the histogram for the intercept term, and remember, the true value of the intercept term is -2, and so that makes sense. That's kind of in the middle of my histogram, but sometimes we estimated higher or lower intercept values, okay? And we can also ask, what's the histogram of our slope term? And again, the true slope value is 3. That shows up in the middle, but again, you know, we're kind of distributed normally around that, okay? And so to kind of plot I'm going to create a density plot of all the different W1, or yeah, intercept and slope terms. And do you think these values are going to be independent, or do you think there's going to be a relationship between the intercept and the slope terms? Okay, and what kind of relationship do you think we'll see? So if we overestimated the slope and we said our estimate for the slope is too steep, do you think will we tend to have a intercept that is higher or lower? Lower, right? And then on the other hand, if we underestimated the slope and it was too shallow, we would tend to have an intercept that is too high, right? So using ggplot, we'll kind of create a two-dimensional density of this. And so let's kind of take a look. And that's what we see. We see a negative relationship between the slope and the intercept. And so these are kind of the 2,000 different plots. This is, we're seeing it's centered around -2 and 3 being the true values here. And we have this thing that looks almost like concentric ellipses. It's not quite, because it's based, this is a density estimate based on our actual data of 2000. If I did probably like 2 million, I would probably get nice, smooth looking ellipses. But that's not what we, you know, with 2000 we still get a little bit of funniness. But we can definitely see the multivariate Gaussian relationship here, right? We're getting these nice, smooth shapes here, okay? And so we can ask, what is the variance of my coefficient matrix, okay? And this is what we get. We got where's this? Yeah. So we're asking, you know, kind of what's the variance or covariance of our estimates of slope and intercept, and we can see there is a you know, kind of negative covariance and whatnot, okay? And here we're kind of just doing this, I guess via like a Monte Carlo way, in that we're just doing a whole bunch of random things, and we're using this to kind of estimate what we're getting, okay? We can also derive something similar mathematically, and this is all shown on page 80 of the textbook, okay? And so I will showing how we can estimate the you know, kind of covariance. So I'll say look at page 80 in the textbook for the derivation of the covariance of our W hats, okay? And anyway, so basically the result ends up being the covariance of W hat is going to be sigma squared times X transpose X inverse, okay? Or this ends up being the second derivative of the log likelihood function, okay? So this is equal to second derivative of the log likelihood function. Okay, which will result in a matrix here. Okay, and you can play around with this code and just see what results. Let me just do it, just something very quickly again. So instead of sigma squared of 0.5, I'm going to do sigma squared of 5. okay? And we'll just kind of run through what happens. So here we get all sorts of craziness because we got the variance can bounce all over the place. And so our variance covariance is much bigger here. Our histograms end up all over the place, and if we plot the density, it's much. We see it looks a lot more crazy, right? So because kind of going back to this plot, we can see just based on the random values that we select, if we have a large error term, even if the true value is guided by 3, -2, because the large values, large variance in our error term can throw off our estimates quite a bit. We're going to get values all over the place, okay? And so, so that all factors into what kind of variance can we expect to see in our estimates. And so, so that's what we have. Okay, so we'll end here for today, and we'll see you guys next week.